All right, this is our lecture video 3.1 to 3.2. We are now in 2 dimensions, and it is getting ready to get fun. So we have displacement, velocity, and acceleration. We've got to define them in two dimensions, okay? Read the notes. Here's the deal. I start off at some location in space, right? Here I am right here, and I have a location of x. Look at the axis. This is x, and this is y in meters, okay? So you can see that I have some location in space at x initial, y initial, and now I have moved to a final location in space, x final, y final. For those of you who are going into engineering, for sure you'll be dealing with 3 dimensions. But okay, so here's my displacement vector, r. We've seen that. We just got finished talking about that. And that is a 2-dimensional displacement vector. And sure enough, I've got some components. I've got components in the x direction, and I've got components in the y direction. So let's take a look at our definitions for 1-dimensional motion. We define the displacement as the final minus initial position. That could be in the x or y, but that's for 1 dimension. The average velocity is the change in position divided by time, and the average acceleration is the change in velocity divided by time. Okay, and of course there's instantaneous velocity as well, and instantaneous acceleration. But nevertheless, now let's talk about what do we have to do for 2 dimension. Well, now instead of delta x, which is the change in position in 1 dimension, I have to have this vector called delta r, which has a 2-dimensional element to it. So I can go up there and actually, find delta r if I know delta y and delta x. There's actually 2 components to that displacement vector, just like we have learned. And we're going to have to break up these problems into x and y parts because we can't solve them at the same time in both dimensions. Okay, so we have to redefine our average velocity. Our average velocity is now the change in position in both the x and y, which is the resultant vector, divided by time. And that is, if we know the average velocity in the x direction and the average velocity in the y direction, we can actually create a little triangle and find that actual velocity in the r direction, we'll call it, okay, which is basically, again, delta r, the change in position with respect to both dimensions divided by time. And then again, average acceleration can be broken into its x and its y. Okay, now all of that is explained in section 3.1, but really we've got to learn how to use that. So now we're into 3.2 because we're going to learn some things about an object that flies in 2-dimensional motion. So 2-dimensional motion, first thing we're going to talk about is a projectile. Okay, so we're going to have a projectile now. Instead of me just dropping a ball or rolling a car across the floor, I'm going to throw a football. I'm going to kick a soccer ball. I'm going to fire a dart gun. Okay, so I want to define what is a projectile. Objects that fly, now this is Mr. P's flipping physics words, through the vacuum you can breathe. In other words, he sucked out all the particles, but we can still breathe in it, but it's really not true. But nevertheless, it's a fancy way of saying 0 air resistance. So we're going to assume that air resistance is negligible. Okay, so if an object is flying through the air with negligible air resistance in both the x and the y direction, it is considered a projectile motion. It's a projectile. A football, a soccer ball, a golf ball. I love sports, right? Tennis, for those who play tennis. An object is a projectile if moving in at least 2 dimensions and is in free fall. What did we learn about free fall? If something is in free fall, it's in the air, nothing's touching it, and we know some things about the object in free fall. What direction do we know that in? We know that in the y direction. So let's review what we know. Acceleration in the y direction is negative g. G is the acceleration due to gravity of the planet that you're on. Let's see, on Earth, G is equal to positive 9.8 meters per second squared. Don't make me sing that silly song. G is always positive, G is always positive. Now, the direction of G points straight to the center of Earth, and if we define down as negative, which we almost always do, that is why we have negative G for the acceleration in the Y direction. There's one of my variables, and I always know it in the Y direction if I'm in free fall, okay? What is the acceleration in the X direction when I'm in free fall? Now you see that I have X acceleration in the X direction is 0, but I want to prove it to you. So the acceleration in the X direction is 0 if I'm in free fall, okay? Here is my pen. You can barely see it. I'm going to drop it. It accelerates downward. You can see that the velocity of the object is changing in the Y direction. What was its initial velocity in the Y direction? 0. I drop it. The acceleration causes it to speed up downward. Therefore, the velocity changed. What was its original velocity in the X direction? Well, it was 0. I dropped it. Did it move all by itself? Was there some kind of ghost in the middle of the air that made my pen fly in the X direction? No. Therefore, there was no change in velocity. It started off as 0 in the X direction. It ended up with a 0 velocity in the X direction. Change in velocity was 0 divided by time. The acceleration was 0. So we're going to prove that. We're going to have to then reevaluate all our kinematic equations, and we're going to separate them out into the X and Y direction. This is the most important statement. The motion in the X and Y direction are independent of one another. I have rewritten it. It is the most important thing. You must separate them out. Now, this is what is crazy about physics to me. You can literally solve the problem in the X direction, ignore what's happening in the Y direction, and then go solve the problem in the Y direction. And then we're going to superimpose those on each other. We can describe it. Now, sometimes we have to find something. In fact, most of the time, we have to use one of the directions to find something. Usually it's time, and then move back over to the other dimension to solve for whatever it is they're asking. All right, so let's take a look at this picture here. We have this flash photography of a red and yellow ball. So what they're doing is they have a red ball. They're going to have a machine that lets go of the red ball. At the same time, they hit a pen and it sends the yellow ball in flying. So they're going to be released at the same time. The red ball is just going to get dropped. The yellow ball is going to have a kind of like a dart gun that shoots it out in only the X direction. Okay, that's the key. All right, the yellow ball is shot horizontally at the exact same time the red ball is released. We know that the objects, both of the objects, are in free fall. Both of them. There's nothing touching it. They're in the air, and we're assuming air resistance is 0. And so we're going to assume we're on Earth. So we have a negative 9.8 meters per second squared in the Y direction pointing down. What is the acceleration of the ball in the X direction? Well, look at the ball. Did it move in the X direction? Its initial velocity was 0 in both the Y and the X. Its final velocity in the X direction was 0. So if I have 0 minus 0 over whatever that time is, it is 0, okay? There is no acceleration in the X direction if it is a projectile. Unless it has a rocket on it, it's not going to accelerate in the X direction, okay? So what was the initial velocity of the red ball in the X direction? We did that. What's the final velocity? We did that, okay? If the red ball, okay, now here's what I want you to know. If the red ball is dropped at the same time that the yellow ball is launched, will they hit the ground at the same time? Well, that flash photography actually is a certain number of pictures per second, okay? And notice the picture actually shows you, and there are awesome videos that prove it to you. So here's my Y-axis, here's my X-axis. Those balls actually hit the ground at the same time, and that is really hard to visualize ourselves. And if you were told that without seeing it, you probably wouldn't believe it. But now that you, well, hopefully you'll get to the point where you believe it, but not only will you believe it, you'll be able to understand why. So let's actually take a look of what's going on in both the X direction, and the y direction of both the red and the yellow ball. So I'm just going to kind of create my little table. Here's my red, and here are my x and y data, and this is my yellow, and this is my x and y. So this is, okay, so what is the initial velocity of the red ball in the x direction? It's 0. What do we know about the acceleration in the x direction? We know that it's 0. So that's an interesting thing. So we'll get to that in just a minute. What's its final velocity then? Well, it's going to be 0, right? Because it can't change. What is its initial velocity in the y direction? Well, here, I always get my subscripts backwards. Okay, initial in the y is equal to 0. We know that. We know that the acceleration in the y direction is minus g, so that's negative 9.8 meters per second squared. And we know, if I knew, I don't know what delta y is, let's, we can actually measure this delta y. Let's call it 1, 2, 3, 4, 5. Let's call it, I don't know, we'll call it 6 meters, even though that's kind of tall, but we'll call it 6 meters, delta y. It's negative 6 meters because it's going down, so its final is lower than its initial, so I'm going to have a displacement in the negative direction. Okay, so I actually have 3 things in the y direction for my red ball. So I can solve for time that it took to go that negative 6 meters, and I can actually solve for v final in the y direction. I could find it. I can find it because if I know 5, 4, 3, 2, 1, if I know 3 variables with my 4 equations, I can solve for the other 2 and become super happy. So here we go on the yellow ball. What was its original velocity in the x direction? Well, they told me that it was shot horizontally. This is a very important phrase. Launched horizontally. Horizon. Some people struggle with the whole coordinate system. Look out across the sun, watch, or the ocean, see the sun set on the horizon. That's your horizontal axis. It is only shot with an initial velocity in the x direction. Okay, so we have some value here. I don't know what it is. Call it, I don't know, 1 meter per second, whatever it is. There's a value that we sent it off at. What was its initial velocity in the y direction? Same as, well, because I shot it horizontally, the only vector related to its initial velocity was in the x direction. This is 0. Okay, let's continue on. What is the acceleration in the x direction? 0. So if that's the case, that final velocity in the x direction has to be 1 as well, because there's no change in the velocity. We'll continue proving that in just a little bit. All right, what do I know about the y direction as far as acceleration? It's negative g, which equals negative 9.8 meters per second squared. And I say delta y of the yellow ball, it's the same as the delta y of the red ball. That's negative 6 meters. Let's see. 3 things. What are the 3 things? 0, negative 9.8, negative 6. Go back over here to the red ball. 0, negative 9.8, negative 6. Can I solve for time over here? Yeah, I got 3 things. Is that time going to be the same? Well, the 3 variables are the same. The amount of time that that yellow ball took to hit the ground is the exact same time that the red ball hit. And that's the reason why. Because its initial velocity in the y direction is the same. It's experiencing the same amount of acceleration in the y direction, negative g, and it fell the same height. Okay? There's some great videos out there. It's kind of fun to watch. Here's this concept represented again by some fun, cool little cartoon. If she let go of it at the same time that he fired the dart gun, assuming they started at the same height, that's critical, they will hit the ground at the same time. I know. It doesn't make any sense whatsoever. Okay, now I want to then take a look at the fact that I will then take my equations that are on my green sheet and change all the little subscripts to have, I can have the subscripts of y, I can have the subscripts of x. It doesn't matter. They all are in the same, I mean, I use the exact same equations. I just use subscript y. Do not freak out about that because the equation sheet only has the x direction. So what? You can use them in the y direction as well. okay? All right, couple things I want to point out. Let's look at what happens to the horizontal. All right, I'm going to show you that we really only have one equation in the x direction, right? So we know that a sub x is equal to 0. So what happens to that? That turns to 0. So if I can bring this down to here, I get the final velocity in the x direction is equal to its initial velocity in the x direction. Wow, that's pretty awesome, but it doesn't really going to help me solve anything. Okay, what about this one? I can cross out acceleration as well, and I could bring this equation down, and now I get an equation that might be able to help me. I get the initial velocity in the x direction times time. Well, how about I just call that the velocity in the x direction? Since the velocity in the x direction isn't changing, I don't have to worry about it. So it doesn't matter if it's the initial, the middle, or the end. The velocity in the x direction never changes. Now I got an equation I can actually use with only 3 variables. So in this situation, I only need 2 things, okay? What about this last equation? Or I'm sorry, the third equation. V final squared is equal to V final squared in the x direction, V initial squared in the x direction. Huh. All that does is tell me that the velocities are the same again, because all I'm going to do is take the square roots and I get the same thing. And then this last equation, again, the initial and final velocities are the same. So I'm really just repeating this equation right here. So the only equation that really helps us in the x direction is this. That is the only equation that will help you in the x direction, because everything else is really kind of intuitive, or it doesn't help you solve anything. But you will have to solve things in the y. Every single one of these. You have an acceleration in the y, you have a time in the y, you have a delta y, you have all of the things, okay? And what I will find is a lot of times is this time, if I'm dealing with one object that's moving in both dimensions, these times are the same. Okay, so I will use information in the y to potentially find time to go over and solve something in the x. Okay, or maybe I will use my x data to find something, find time. Time crosses both. So time will go back before, time doesn't have a dimension, it's a scalar. It's applied to both the x and the y. Okay, that's the only thing that crosses over. All right. I'm getting close to the end. I know this is a heavy lift. So, important facts again. Air resistance is negligible. The horizontal component of the velocity Vx remains constant, does not change, because there's no acceleration. Okay, the vertical component of acceleration, so that's a sub y, is negative g, because I'm in free fall. Okay, I'm in the air, nothing's touching it. The vertical component of the velocity and the displacement in the y direction are identical to those of a free falling object. That yellow ball's behavior in the y direction alone, if I were to draw a position versus time curve in the y direction, it would be exactly like a position versus time curve for something just free falling in the y direction. Okay, because the x direction of that yellow ball has no impact to its behavior in the y direction. They are independent to one another. Okay, projectile motion. Now, here's this kind of projectile motion can be described as the superposition of 2 independent motions in the x and y directions. That's hard to see. I know that sounds fancy, and I'm not sure that I would use it other than, okay, I believe it based on my knowledge. This is one of the most important graphs. If you understand this graph, I mean, really understand this graph, you're going to be coming a long way. So here's what I mean by that. So I get told an initial velocity. Here's my initial velocity vector. Okay, let's circle that in. I got some initial velocity vector at some angle above the horizon. Break that initial velocity vector up into its original. I don't like the subknots, even though that's what they use. Its original velocity in the x and the y direction. All I need is 2 things of that triangle, and I can solve for everything else. Okay, what is happening to the velocity vectors? Notice the length of the x velocity vectors. Notice they're not changing. The length of those vectors, remember the length is the magnitude, does not change, okay? They did not change because there's no acceleration, therefore the velocity stayed the same. But what's happening to the y? Let's do that one in purple. Look at the y, he's longer, now he got shorter, and notice at the very top, as we know, if it's in free fall, the velocity at the top in the y direction is 0. Okay, so if I threw that pin up for that nanosecond at the very top, the velocity is 0 at the very top. But which direction is it 0? It's 0 in the y direction. Now, as it goes back down in the y direction, the velocity flips signs and starts to get negative and becomes more and more negative, and then eventually gets to the very bottom. Because this ended up at the same height, the original velocity and the final velocity have the same magnitude but opposite signs, and so this vector, this final velocity vector, is identical in magnitude as the original velocity, okay, just with an opposite direction, okay? So let's kind of continue with this explanation. I will continue in just a sec. I'm gonna take a break. Okay, continuing on. So I have a projectile that's launched with a speed of 15 meters per second horizontally. That's a very critical word to pay attention to, that word horizontally. And I have actually sketched. So it says draw a sketch, label the origin, label the axis. So here is my sketch over here. I have a cliff. Now I'm going to make it interesting. I'm going to actually throw it and send it to the left originally. Okay, so I have my origin right here. This is my x equals 0, y equals 0, right? And I have some height that it starts at y equals 100 because I started off at 100 meter tall cliff, and so I'm good. So I've done part A. Now, what is its initial velocity? Okay, initial velocity. Did they ask for the initial horizontal velocity? No. Did they ask for the initial vertical velocity? No. The initial velocity happens to be in the horizontal, so I can say negative 15 meters per second, or I can say 15 meters per second to the left. Okay, I like that. What's the initial speed? Remember, the speed is the magnitude of the velocity, and there's only one answer in this situation, and that would be 15 meters per second. So in other words, if I'm negative 15 meters per second, my speed is 15 meters per second, okay? Driving down the road 100 miles per hour north, I'm driving down the road 100 miles per hour south. Don't they have the same speed? Yeah. What is the initial horizontal velocity? Now I'm actually asking for the horizontal. Well, that's exactly the same thing that I just said. So I will say negative 15 meters per second, or 15 meters per second to the left. What is its initial horizontal speed? Same thing. You'll see why I'm breaking those up in a minute when I start going at an angle. What is its initial vertical velocity? Well, there's an interesting thing. I launched it horizontally. What was its initial vertical velocity? 0. What was its initial vertical speed? 0. In what direction do you have enough data to solve for things? Well, I don't know. Let's do our table. Here's my x, here's my y, delta x, b initial in the x direction, b final in the x direction, a in the x direction, time. Time is not the direction dependent, it's a scalar. Delta y, v initial in the y direction, v final in the y direction, a in the y direction, and time. That time, actually, a lot of times I will, to help, that time can be right here in the middle. Okay, that time is the same. That's the only thing that crosses over into both dimensions. All right, do I know the original delta y, or how would I, relative to, how would I have enough data to, where do I have enough data to solve for how much time it took to hit the ground, for example? Let's talk about that. Well, delta y is a negative 100 meters. I wasn't very clear in the question, I see. The initial velocity in the y direction was 0. What was its final velocity? I don't know. What was its acceleration in the y direction? Well, it's in free fall, so negative 9.8 meters per second squared. Okay, look, I got three things. All I need is three things, 5, 4, 3, 2, 1. So I've got three things in the y direction. I can solve for time. I can solve for the final velocity of that projectile, whatever it is, right when it hits the ground. So here, right before it hits the ground, don't tell me the final velocity is 0. Okay, I'm talking about the nanosecond right before it hits the ground. All right, how would you solve for the distance away for the projectile would land? How would we solve for the distance away from where it started? And which direction does that mean? That means in the x direction. Well, if I have three things over here in the y, I can find t, and then I can come over here, and what is the only equation that's going to work for me in the x direction? Vx times time. So I was given the initial velocity of 15 meters per second. We forgot to fill this in. I don't know this. We really only have one velocity in the x direction because this is equal to 0. Okay, so we're going to now use the time that we solved for in the y direction and the initial velocity, and then I can solve for delta x. Okay, moving on. What if I have a projectile now? Now it gets a little more interesting. I'm going to make it even more interesting. Here's my cliff. I have 100 meters again. Here's my origin, 0, 0. Okay, I'm going to launch it with a speed of 25 meters per second at an angle of 30 degrees. We'll call this angle 30 degrees below the horizon. Okay, so draw and label the axis. I did. What's the initial velocity? Okay, I didn't ask for the initial horizontal velocity. I did not ask for the initial vertical velocity. I asked for the initial velocity. That is not the component. That is the resultant vector. That is 25 meters per second. That's the magnitude. Velocity has two things. At 30 degrees, I could say below the x-axis, or below the negative x, or at 30 degrees south of west, based on how I drew it. Okay, that was its initial velocity. What was its initial speed? Well, speed is just the magnitude of velocity, 25 meters per second. Okay, speed is equal to the magnitude of the velocity. Okay, instantaneous speed is equal to the magnitude of the instantaneous velocity. Didn't have time to do any curving around. Okay, all right, what is the initial horizontal velocity? I have just asked you for a component. Okay, I have the initial velocity was 25. This is its velocity in the y initial. This is its velocity in the x initial. I have just asked for the horizontal component. Okay, I said it wrong. I was thinking correctly. Let's try it again. I had my x's and y's mixed. All right, never mind that. Here we go. This is my angle. And what did they tell me that was? That was 30 degrees. I have two things of the triangle. That's all I need to know. If I want the horizontal, that's the adjacent side. So cosine of 30 degrees is equal to the adjacent side, which is what I want, over the hypotenuse, which is 25 meters per second. I find xi equal to 21 point, okay, let's try to 21.7 meters per second. Now, that's what your calculator gives you. Now, based on the way I drew this, remember, because we don't use standard position like pre-cal, it doesn't spit out that negative. You actually have to use your thought. Draw, is that a negative or a positive? Well, it's moving to the left. In the x direction, that's a negative. Okay, what's its initial horizontal speed? Magnitude of the horizontal velocity, 21.7 meters per second. What is its initial vertical velocity? Now what I'm asking for this guy. Let's go back, and horizontal is this one. horizontal, vertical is the down, the component in the y direction, and so that is opposite of that angle. Sine of 30 degrees is equal to what I'm looking for, the opposite side divided by the hypotenuse, meters per second. I will find the initial velocity in the y direction to be 12.5 meters per second. That's what your calculator is going to tell you. Now you got to be smarter than the calculator. 12.5 meters per second. Is it going down? Yeah, it is. And we're going to define down as negative. So it is negative 12.5 meters per second, or 12.5 meters per second down. What was its initial vertical speed? So let's do our speeds in green. Vertical speed. Well, it is the magnitude of negative 12.5. So I don't care what the direction is. I know that I'm at 12.5 meters per second. Now you understand why I was asking all those weird questions over and over again. Okay, people struggle with the question when they're asked for a velocity. If it didn't tell you horizontal, or if they didn't tell you vertical, you better make sure you're thinking of the resultant, or the one that contains both the x and the y, assuming that it's a projectile. If they say horizontal, then I know I'm in the x. If they say vertical, then I know I want the velocity in the x or y direction. In which direction do you have enough data to solve? I don't know. Let's go and line them all up again. I have x, I have y. What do I know? I know Vy initial is equal to, let's see if I can find it, negative 12.5 meters per second. I forgot out my delta y. I don't know my final velocity when it hits the ground in the y direction. I switched that up a lot. I don't know that. I just know that delta y, what is this delta y? Well, the cliff is 100 meters again. I started at 100 meters up. I find a final location is at 0 in the y direction. 0 minus 100, I get a negative 100. So I have a negative 100 meter displacement. I happen to know that it's in the air. What does that mean? I am in free fall, negative 9.8. Try it again. Negative 9.8 meters per second squared. That's 1, 2, 3, 4. What's my fifth variable? That's time. I can put it on the bottom because it's going to cross dimensions. It's crossing over. It's got all kinds of power. All right, what do I got going on in the x direction? Delta x, I don't know. I have no idea. Initial velocity. I actually have an initial velocity in the x direction. We solved it. We found it to be minus 21.7 meters per second. That means it's to the left. What do I know? I know that that velocity is going to be the same. So I can just call that the velocity in the x direction. It is not going to change. Why? Acceleration in the x direction is 0. What is the definition of acceleration? The velocity in the x direction final minus the velocity in the x direction initial divided by the change in time. This is not 0. This value is 0. And how is that value 0? Because the velocities are the same. It does not accelerate. Okay. All right. So we know that this is 0. And so the only equation that I have to work with in the x direction is that delta x, the velocity in the x direction. You can call it initial, you can call it final, you can call it Vx, times time. So I don't really have enough information in the x direction to solve it. And so what I have to do is use my y, because how many things do I have in the y? I've got 1 variable, 2 variables, 3. I got 3 variables in the y direction. I can use the y direction to solve for time and then get my time value and come over here and solve for whatever, x. Okay, so in the y, I have enough data in the y direction. How would you solve for displacement in the horizontal? Solve for time in the y, then solve for delta x. Okay? All right. Try to see how much more I have on this. I'll stop now. I have a couple of brain teasers on these, and I'll do that in a separate video. All right, that's it. We got some, we're basically going to apply this knowledge by working problems. They're going to get interesting, folks. All right, message me if you have any questions.